Little bit of background, I guess, on Docker. So you've probably heard of virtual machines, and you've heard of virtual environments if you're doing Python. And so Docker is somewhere in between these. And sometimes we'll call these containers. Okay, my handwriting is awful on this thing, so I apologize. So what a virtual machine is you've got some host machine. And that host machine is running some operating system. So maybe it's Windows. And inside that Windows operating system, you have a fake machine running, and that could be running Linux. It could be running Windows, and you can have multiple ones. And you can have as many as you want. Well, I mean, subject to the limit of your hardware, right? So we call these the guest operating system, and this is the host. So it turns out that, as far as this operating system, this version of Windows is concerned, or this version of Linux is concerned, they don't know that they're running inside a virtual machine, right? So they're kind of oblivious to that because there's a program running in here inside Windows that is providing them an illusion that they have access to a full physical machine. So it tells them, oh yeah, you've got this hardware network interface, and you've got this much memory, you've got this much CPU, and it's lying to them, right? So that's how virtual machines are working. And so this is how we use, AWS EC2. Okay, so if you've ever played with any of that, those are what those virtual machines are. What they do with EC2 is they've got their host, and then they'll actually sell guest operating systems to people who don't know each other, right? So we could be on the same physical hardware as our competitors, and that's okay, right? Because we're not sharing any. I mean, we are sharing the physical resources, but as far as we're concerned, we've got exclusive access to the machine. As far as they're concerned, they've got exclusive access. Virtual environments is just Python, right? So there's no security isolation here. Containers are kind of an in-between. So what a container is, and the way that Docker is actually working, is there's some funky things that it does for Windows sometimes, but we'll focus on just the Linux version. So we've got Linux as our operating system. And let me think about how I want to show this. Well, so let's think about some operating system resources. So we've got CPU, right? We've got memory. And we've got network interfaces. Right? So those are things that the operating system kind of manages for you. And it tells you what's available when you're writing your program. But then there's also other things, like there's a file system. And there's, all the different processes have process IDs. And there's users and user IDs and groups and group IDs. So these are all things that operating systems normally are kind of managing for us. What containers do is you still have Linux running, and that's the operating system. But what they do is they segment out some of the stuff, so it provides you it almost looks like you're your own operating system. It's not quite as separated here. But you have maybe a quota for CPU, although that's optional, and memory, I'll call it RAM there. We've got our own, what's called a virtual network interface. And so this is Docker. And you get your own processes, so process IDs, user IDs, and group IDs. And what Docker does is it kind of maps the real stuff inside the main operating system to what the fake stuff is inside this container. And I'm not physically hand waving yet, but I'm getting close. So what you won't see is you won't see a Linux host running a Windows operating system or a Windows host running Linux, although, like I said, they do some funky stuff with Windows. When you do this on a Mac, for instance, they actually have a Linux virtual machine that you run on Mac. So if you actually look at this on a, if you're trying to run Docker on Mac, Mac OS is here, and then they've got this. It's like X. I don't know exactly what the, but there is a virtual machine running Linux, and then you have little containers running inside there. So they still provide that Linux layer. If you're on Windows and you're using Windows services for Linux, then it's basically Windows plus Linux is what your main operating system is, because that's what WSL2 does. And so in that case, you have your containers that are kind of running inside there. And if you've got the older Windows services for Linux, it's more like a Mac. So this would be, actually, if it's not WSL2, I should say, you would have Windows, you have a virtual machine, which is running Linux, and it's got its containers inside there. Okay. So I just wanted to kind of give you kind of the lay of the land before we get into the details. So any questions about kind of the way that we're kind of isolating these things from one another?
I guess I have a question about that first, or not the OS resources, but the box that you drew on the left.
This one right here?
Docker and Linux, yeah.
Yeah.
So is that not a virtual machine within a Windows machine? Or I don't understand why Docker's on the outside, basically.
Sorry, this one, which one are you talking about? So there's no virtual machine involved here. So what it is the actual Linux operating system has the ability to, inside Linux, isolate these containers from one another. So that's kind of a native feature of Linux.
Okay.
And that's how Docker works. It's going to be using that native feature to isolate and provide visions of, like, it's some of the OS resources are virtualized, I could say.
Okay.
But not the whole
thing. I thought
thing.
that you were giving an example of Docker within Linux, but you're just giving an example of Linux, I guess, there.
Well, Docker uses this feature of Linux. That's how Docker works.
Oh, okay.
Yeah, that's what containers really are, is they are, there's actually a couple of, I know that there's a thing called C groups, and then there's another thing, which is a feature of the Linux OS that Docker uses to give you some somewhat nicer tooling on top of kind of the raw C groups that it uses to create these containers and this isolation.
But all of these systems are using the same Linux. So if you have Docker on Mac or you have Docker on Windows, it should be able to, if it's working, it should run, the container should be able to run on either operating system the same.
Yes. So you should be able to run the same containers on Mac, Linux, and Windows. That should be the case. And we're going to kind of pretend like Windows containers don't exist, because I don't know exactly how they make those work. But this is the general idea. Now, I think one of the things that helps to maybe understand this a little bit better is to talk about what an operating system actually gives you. So there's really two main parts that we talk about with operating systems. There's what we call the kernel, and then there's a whole bunch of files. And those files will be all of your operating system tools. So things like Bash, or if you're on Windows, CMD, or PowerShell. And somehow I just switched over to a different tool. PowerShell. We have other files. We have, anything that's under etc, password. So these are all of the things that Well, these are all just files that are running inside the files, or that could run inside the file system. But the kernel is kind of is the controller. So it is a file. It does exist, but it's a program that's always running. So the way that most of the operating system works is you got your machine here. The kernel is going to sit here at the bottom. Kernel. And it's responsible for giving you access to all of your hardware. So network, if you need to allocate memory, if you need to start a process, start or kill a process, create actually as users, I'm not sure if those are handled there as well. We've also got our file access. All of that's going to be mediated by the kernel. So the kernel is kind of providing an API, if you will. So there's different places where you can call into the kernel. And the kernel has full access to the actual physical hardware of your machine. Or if you're on a virtual machine, it has full access to the fake physical hardware, the virtual hardware. The kernel is kind of like, it's the controller, it's the super user. It has full low-level hardware access. Now the programs up here, we'll call this actually user space. We'll call this the kernel space. So things like bash, that's just a program that is making these calls into the kernel, right? So it's asking for the kernel to maybe write a file. Kernel writes into that file and it sends the results back into bash. Right, so there's communication that's happening there, and all of these things are happening through, and sometimes we'll call this a system call. Okay, so that's really what the kernel does. So a kernel, you might have seen people say it is, some people who are really maybe pedantic will call it, they'll say it's not Linux, it's GNU Linux. You might or might not have seen that. So this is people saying, well, Linux isn't really a thing. Linux is just the kernel. And GNU is all this other stuff that runs here. Because, Linus Torvalds had nothing to do with creating bash. That was some other dude. And Linus had nothing to do with GCC, which is a compiler. That's also something that's distributed with all of these Linuxes. So that's why we have things like, we have Ubuntu. Ubuntu is a distribution of Linux. So it uses the Linux kernel, but it's got its own set of tools and its own set of programs. And then we have Red Hat. And we have Alpine. And so each one of these will make different decisions about what runs up here, but they're all using the same kernel. Does that make sense?
Yeah, I think that does.
Okay. So it turns out that the kernel is what's providing all of these features that allow us to do separation of what we've called the Docker containers. So what a kernel or what a container gives you now is, I guess, inside a container, we have a file system. That's kind of one of the built-in things that you're always going to have. So as far as you're concerned, you have access to all the way back to the root of the file system, right? Nobody else is running there. It also gives you some a mapping of process IDs. So when you start a process, it has a number that's associated with it. Now there's a real process ID, and that's what your operating system actually knows it as. But if you're running inside a container, it maps it to a different set of numbers. And so whenever you start a container, the process ID will be process ID number 1. Well, process ID number 1 that's actually a special process ID over in the operating system, which is called the init process. It's whatever it boots up first as that first program. So your process ID 1 in the container might be, 632 in the actual host. Okay, so there's a process ID mapping. There's also a user ID mapping. So the set of users that have access to the container could be a different set of users than have access to the host. And you've got, and the same thing applies to groups. And you also have different networks. And that just says, I want to bind to, my first network interface, or I want to use, I want to send something on an IP address. Well, Linux provides the ability to set up what's called a virtual network. So it's just a fake network that's all running in software, right? It doesn't actually even need to use your physical network. You could have containers that are communicating with each other, and it never hits a Wi-Fi or an Ethernet or anything like that. Okay, so these are kind of the basic things, and then we can also give it quotas. We don't really do this much. And quotas would be for memory and CPU. And so you can give limits on that and make sure that your container doesn't get too big. Okay? So, and that's all the responsibility of the kernel. So we don't do any kernel programming, by the way. Even if we were doing C programming, we wouldn't be kernel programmers. We would be writing we can write C programs that run in here. Python is a C program that will take your .py files and interpret them and run them. But the actual program that's running is Python, right? As far as the operating system is concerned. Right? So Python is making all these system calls on your behalf. Okay. So I know it's kind of we're not just talking about Docker, but it's kind of a little bit of background of OS, because I think it helps to kind of have this mental model when you're looking at these things. So now let's talk about what a container actually looks like. Well, actually, so when you've got Docker going, you still have this Linux machine as kind of your host. Linux has a kernel. And the kernel has the ability to manage containers. So call it C1 and C2. And those containers, they're just groups of processes. They're groups of programs that are running that have this faked out file system and user ID space and process ID space and maybe a network as well. Right? So the kernel's responsible for managing these, and I'll make that a fat arrow to indicate that it's got control over them. There's also, if you're doing Docker, there's another program here called Dockerd. And Dockerd makes system calls, and it asks the kernel to do certain things with these containers. So it might say something like, hey, please start a group of processes with this information. And it's responsible for managing all of that. Now, when you actually run a Docker command, what your Docker command does is it sends a message to Dockerd, and then Dockerd has the kernel do some things for you. So that's kind of the way that these things happen. That looks like Dockerd or something like that. Anyway, it's supposed to be a Dockerd. So if I were to say Docker run Ubuntu, that's actually not directly telling the kernel to do anything. That's telling the Docker, and the D here stands for daemon. And we spell it like that so that it's not, doesn't have as many of its religious connotations. That just means a background process, right? So the daemon's running in the background. And so you'll see that a lot in Linux type things. So anyway, what this is actually saying is, hey, find Dockerd, please find some, and this is an image name actually, find this image and use it to create a new container, and please start it up for me. So that's actually and then Dockerd is going to figure out what commands it needs to issue to the kernel to create a container that's running Ubuntu. Okay? So what's an image? I guess there's two main things that we need to understand about about Docker, we have containers. And a container is that thing that is, it has some processes. And a process is just a program that's running. And it can have more than one. So either one process or multiple processes. And all the fake UID, GID, and file system, and all the other things that we can fake out inside that container. So that's what makes it a container. What an image is it is a template for making containers. And so what an image gives you, the main thing that an image gives you is it gives you a file system. So think of it like a zip file. Right? So it's just all the files that it needs to create inside that container. Or when you're going to create a container, it's going to make, basically the container is going to start out with these files. There's other things that an image stores, like what program do you want to start up when you start the container, or different environment variables to set for that program. But that's the basic idea of the image. So there's a lot of images that you can get from different places. The main place where you get images is you can download them from a repository that Docker provides called Docker Hub. And we use Docker Hub as the basis for some of our images. Okay? So containers and images are the two main things that we're going to deal with in Docker. Right? Container is always something that has these processes and all this fake stuff, and then the image is a template for making new containers. Now, you could have a container where the processes have all died, or you could suspend a container or something like that. But think of this as something that's running right now, and it has resources allocated to it. It's got a fake network interface. It's got its own file system and everything. And it could be changing things in that file system. Whereas an image is just a static snapshot of what you could use to then later make a new container. Okay? So when you are, the way that a container actually works is, and I'm going to focus mainly on the files, is there's two parts to the file system. So there's the part that the image gives you, and this is going to be from the container. So there's the image, and then there is, and that's a read only. And then there are the changes, and that's read write. So the container is running, it's probably making changes to the file system in some way. It's creating files, deleting files, modifying files. And so what it would do is, say you had some file foo that was, foo.txt. Sorry, that was supposed to be another T. Foo.txt here. And then my container program changes foo.txt. What's going to happen is that's going to have another copy here. And why do I keep saying TXX? I don't know. So if it sees this file here, it's going to use this instead of this one. Okay, so we'll call this the layered file system, because there's these two layers. Whatever changes the container makes, they go into this read-write layer, but whatever it got from the image, this is in this read-only layer. This is like, we start off with the image, and the read-write layer is empty. We make changes, and as we make changes, this read-write layer starts to accumulate files. All right. So that's the layered file system. And that is the case for almost everything. There's also one other thing that is kind of a neat thing that Docker does, and that is we can have volumes. So that's most of our files. But then we have volumes. And what volumes are is it's a directory that does not using the layered file system. And the reason is, so when we're working with our containers here, one of the things that we might want to do is, let's say I'm building a container for the database, right? So I install a bunch of packages in that container, and then there is actually a command where I can take a container, I can shut it down, and I can take this layered file system, and I can actually take this and I turn it into an image. And that command is actually called commit. So let's say I'm building a database and I commit that image. I probably don't want to actually commit the files that they're inside the database, right? I don't want to, like, if I've created some test data inside the database, I don't want to have that test data be part of the image. And so what I would do is I would say, well, maybe the let's say the var db is a volume. So what that means is, instead of tracking those changes here, it would actually track them. It doesn't even track them, really. It's just a volume, right? So anytime I do a commit, that volume does not get committed. So my changes to that particular directory don't get saved. Now, what volumes can't? So you have volumes. So that's just volumes in general. But one of the neat things you can do with volumes is you can map volumes to the host. So I can say I want, say, home Rick source on the host to be a volume src in the container. And that's what we do a lot, actually, with our containers. So we'll map the current directory where we've got all of our application code to something called /app.
So what read or write access do we have with volumes, I guess?
So it depends. So you have whatever access that, so if you do a regular volume like this, then it's just, Docker is going to give you the same access that it would have. It's just as though it were a change inside the layered file system. Docker generally runs, like, the Docker daemon will run as root, and most of the time, even though it's maybe not the best practice, when we are using containers, like if you just do a Docker exec or something like that, you're going to be going into that container as root, meaning you're the super user and you have full access to everything. Now, the containers themselves can have their own user space, and so you could create an unprivileged user and restrict access there. But generally speaking, you're going to have full access to everything in the volumes. So, and this would be like source TCPA. That would be going to /app. Okay, so it's just mapping this directory in the host to a volume in the container, and that way I can make changes in the host and the container immediately sees them. Right? It's like you're having a network file system almost, except there's not really a network involved.
And so a volume, it's not really that it's not a layered file system. It's just kind of outside of not outside the container, but
well, it is outside the layered file system. It's not a layer which will be committed to the image.
Yeah.
So I guess that's the technical way to define it is part of your file system that is marked as don't put this in an image, right? But then one of the nice features is you can actually have those volumes which are also mapped back to the host. And so we actually use some volumes that are mapped and some volumes that are not in our code. All right. So layered file system. Yeah, so I'm trying to think if there's any other main things to talk about before doing a little demo. Okay, I think that I can probably show some of the things that we can actually code with now. So let me switch what I'm sharing. All right. So there we go. So let me just go into, actually, let me not do that. There. Let's go to my source directory. That's a reasonable place to go. Okay, so Docker, the commands, remember, this is going to communicate with the Docker daemon. And so one of the things that I can ask the Docker daemon about is, what are all of the images you know about? So I can say Docker image ls. So these are all of the images that Docker knows about, things that it has dealt with. So you see a lot of Docker images that deal with AOF. So these, it calls this a repository. Won't worry too much about, well, I guess I can talk. The repository, this is if, so I've been trying to keep everything local. Repositories are places where you could push an image to, or you could pull an image from. So it's a lot like Git in that way. So when I push an image to a repository, it goes up there. Some of these, like this Alfred Knows right here, this can't be pushed because this is just a local image name. However, this can be pushed. This is a full path to a repository on Amazon, right? So this, I can actually take this, and it turns out these are both references to the same actual image. So when I look at that thing in the middle, that's the image ID. That's going to be the important thing that actually identifies what's in the image as opposed to other things. But then it's got different names, right? So AOF, AOF prod latest, and this AOF prod latest are all the same image, right? Does that make sense?
So is it kind of like in Git having, the local, I don't know, branches, I guess, and remote branches, and the
kind of.
image ID is kind of, the reference for the same thing, but the repository name is a little bit different, with having origin at the beginning.
Yeah, so the way that Docker is actually going to work is it's got what's called a tag associated here. So these things over here, even though it calls them names, or it calls them repositories, these are actually just tags that are associated with the image. And so this name, actually, well, it's the repository and the tag together refer to this image. And so that's the data that's stored in terms of the naming goes. And then there's also, like, all the images are known by their image ID. That's the primary way that we look at them. And that is going to be the same for any image that has the same contents. And so it's kind of like the SHA when we talked about Git. So let me see if there's other. Well, let me just look at AOF. So that's an image that I've worked with. That's the Arborian auth. You can see that I've got, I really just have one image that I'm working on there. So let me see if I can do digest as well. Yeah, that's actually doesn't give me anything. But anyway, that's an image. I can say Docker image ls Ubuntu. So I have an Ubuntu image. If I didn't have an Ubuntu image, I could actually say Docker pull Ubuntu. And if I don't give a repository here, it's going to go to Docker Hub, which is Docker's own repository, and try to find something that's publicly accessible called Ubuntu. Also, it says it's actually already up to date, so you're good. Okay, so those are my images, right? So, or I can look at all of my image. Actually, let's look at TCPA. There's a couple of TCPA tags here. Now I also have I also have containers, and so I can do Docker. Can I do Docker container ls? I indeed can. I wasn't sure if that would actually work. I'm going to zoom out just a bit so it doesn't wrap there. So it turns out I've got a couple of these that are going on. I've got some AOF stuff here, and looks like that doesn't really need to be going, so I might delete that after a while. This is my health drive stuff. So I've got a couple of containers here. One is the base health drive, and the other one is, this is actually SQL Server. So Microsoft provides a free version of SQL Server that runs in Linux Docker containers, which is kind of, man, if I'd said that 10 years ago, nobody would have believed it. So anyway, that's these are some of my containers. If you do an ls-a, it shows all of the containers that are also kind of exited already. So it kind of keeps those file systems around in case you want to look at them or do whatever with them. You can purge those if you want to. You can remove containers. And then some of the things that you might do as just shortcuts would be like docker ps. And that's ps is a command to get processes. This is just the same as docker container ls. Right? PS is the older command before they created the container subcommand. Or docker images as opposed to docker image ls.
So is it, I don't know, this is probably not entirely true, but is it kind of fair to say that an image is similar to a commit in Git?
It's kind of similar to a commit. Yeah, in fact, to create an image, we can use the command commit. So let's do a simple little image here. And I will run a, call it tech talk. So I can name my containers when I run them. And I'm going to just run the Ubuntu. And I have to give it a command. I have to give it an initial process. If you don't give it an initial process, then it'll just run a command that quickly exits, right? So it's kind of a useless thing. So I will start a process here, and I'll just do bash. And I'm actually going to do another couple of arguments here. This makes it interactive and make sure I get a terminal. So if I do this, I now have, see, I'm, well, I can say, who am I? Not whammy. I'm root, right? But I was just logged in as Rick446. But inside the container, I'm root. So that means that somehow this, container has different, it's done a mapping here. If I look at all the processes inside the container, there's process ID number 1 is bash. Let's actually, if I look at the processes here, well, that's very different, right? Those numbers are much different. This is in my main Windows, Windows services for Linux. So I could even say, there's another command here, docker top. Oh, I actually got to give it the container name, and I called that tech talk. So this is telling me that the number 1 process in tech talk is bash, and that its real process ID is 7665. Right? So Docker is mapping those process IDs for us. All right, so I've got this, and let's say, let me go into my home directory here. That's in /root. Actually, there we go. I'm in the container now, and I am going to create, actually, I'll just use echo. This is a file to test file.txt. Okay, so I've created a file. Right? So now I'm going to exit this container. Okay, if I do a docker ps -a tech talk, can I do that? No, I can't do that. Do ps-a and then grep tech talk. So tech talk is there, but it's exited. Right? So show that up. Still too big. Okay. So that's the container ID. This is the name, that's the image that I made for it. And then the name of the container that I assigned to it. So one of the things that I can do with this container is I can commit it. So let me just remind myself. Yeah. So docker commit tech talk, and I'm going to commit it to tech talk image. Okay. So what that did is it took the read-write layer that I had on the top of that layered file system, and it turned it into a read-only layer and built a new image based on that. Okay. So if I now look at my docker image ls, I'll start anything, well, tech star. So there's now a tech talk image that I've just created. So now if I want to do a Docker run, run, I'm going to do a --rm, and that'll make sure that it removes the container when I'm done with this. Okay, so I'm now inside that Tech Talk image. Let's go to my home directory. There's a test file, and we see that that test file has already been created. That's what I saved in that previous copy.
Okay, so with containers, like those are like temporary like things?
Yeah, they're kind of like a program while it's running.
Okay.
But it's not, yeah, it's not something that you can move between machines very easily. What you would want to do if you needed to move it is you would commit that container, which takes all of the changes to your file system and puts it into a new image.
Okay, so it's like taking something, like putting it in a box, like putting a bunch of books in a box and then moving it somewhere else, taking the books out, sort of thing. Okay.
Yeah.
Okay.
Yeah, exactly. So, and then if I exit this, the thing that I just ran is not going to be there anymore, because I said --rm. So, right, that's the only container called Tech Talk is right there.
So how do you flag something to, or how do you make something a volume so that it's not going to be committed? So
to make something a volume, I can actually, well, here, I can do this on the Tech Talk image. There's a -v for volume. And I think if I just give this, call it my vol. Yep, so there's nothing in my vol. So let me go into my vol. Actually, I should not have done that with a --rm. So, okay. Okay, so now I created a file inside that my vol directory. Right. So I'll exit this, and I don't even know what that. I should have given that a should have given that a name. So the name of this container was Practical Lovelace, because Docker gives us nice little container names if we don't give it one. So I will commit that. And I will commit it to Tech Talk image 2. Okay. So let's do a Docker image ls TechStar. So those are very similar, actually. Let me see if, so there's a command, image history. I think it's image history. Is that right? Yeah. Let me go full screen there. Okay. And then if I do 2, okay, so it did pick up some changes, probably just my bash history. That's what this extra image is. But the interesting thing I want to show with the history is I kind of lied when I said that there's a read-only layer. There's a lot of read-only layers in images. It's a layered file system. So the way that this was created is somebody started up a container and they ran this command. And that actually created a layer of 72.9 megabytes. And then somebody built a container based on this image, and they ran this command. And that created a layer of 811 bytes. And then somebody started up a container based on this image, and they ran this command. Right? So it's basically they're running a command, committing it, running a command, committing it, things like that. And so each one of these gets saved as a separate layer. When you do a Docker pull or a Docker push, Docker is actually going to look at those layers and see does it already have a copy of this layer or not? So what that allows me to do is, if I needed to go over to somebody else's machine and take this Tech Talk image too, if you already had the Ubuntu layer, this layer right here, you don't need to pull any of that. You just need to pull all the changes that I had in these 2 layers. Okay? And then I think I might be able to do a -v. I don't know. No. How about dash on here? Nope. I'm just trying to see if I can get the actual. No, it's not going to tell me all of the details about these, but it does at least show me the image or the layers that were created. Okay, so now if I run something based on run this based on TechTalk image 2, and let's look down in my vol. Nothing there, right? So the file that I created is no longer there. Well, what if so in this case, I had my vol specified right there as a volume. What if I don't use that? Is it going to be there? Nope, empty. So still nothing there. It kind of remembers that there was a myvol directory because that's what I committed. When I committed it, it knew that there was a directory there because there was a volume mounted, but that was the only thing that it knew.
So that file, is it like permanently lost then? Or is it?
It's pretty much lost. So you can actually say volume ls. And so there are volumes. Which one I just did, I'm not sure. So let's look at the PS. PS-A. I had, Practical Lovelace. That was the one where I was, that's the one where I had the volume mounted, I think. So I can actually inspect that. So this will tell you lots of information about that image. And let's see about my vol. Okay, so that one did have the volume attachment. So if I restart that, can I restart it? Let's just try this. Nope. I am not sure if I can resume this one and get. Oh, so I can. Oops. So it's not dead. It maintained it, but only because I still had that container running, or only because I hadn't removed that container. So the container still had a reference to the volume still had the data in it. And if you know the name of the volume, it doesn't lose it at all. All right, so you can actually give volumes names, you can create volumes and things like that. So here I will remove Practical Lovelace. And so now the volume would be very difficult to find. Like I'd have to look, I could look through all of these volumes if I really wanted to, but that would be a pain.
So you don't really want to create volumes within a container. You really just kind of attach a volume or map it, to existing directory in your computer.
When you're running the container, or when you first start up the container, you tell it about any volumes you want to be there. And so that was a volume that didn't map anywhere. But it can also have something that does map somewhere. So let's do this based on TechTalk image. And so what I want to do here is I want the myvol inside the container to be mapped to home. Rick. Oh, come on. Oh, I can't do completion because of the colon there. Okay. I'll do source. Actually, let's do source. Let's make it /src instead. Okay, I must have done that backwards. Yep. Hate it when I get those backwards. Okay. Okay, so that's a directory on my host that's now mapped into the container. And that's one of the ways that we can get data into the containers. Right? So when we're running something and we're testing it and we're developing something, we'll usually have our current directory mapped into the container because we want any changes in our Python files to be immediately visible within that container. All right. So two other things I wanted to briefly mention. are, let me clean this up, image, rm, tech talk image, tech talk image 2. Now, when it untagged tech talk image 2, it recognized that all of these other images don't have any references to it anymore, and it cleaned them up. Right, so all of those changes went away. So now let's go into the DevOps. I want to talk about Docker files. So, that's not the right place. This is a Docker file. You might have seen it before. What this is its instructions to tell Docker how to build an image. Let me tell you what Docker is going to do when it sees this. So number one, it says from Alpine 3.10. That means go out and pull the image from Docker Hub called Alpine with the tag 3.10. That's going to be the basis for this image. And you're always going to start your Docker files with a from. Then there's a bunch of run commands. For each one of these run commands, what it's going to do is it's going to start up a container, execute this command, and commit it as a layer. So that's why you'll see people have these crazy, awful long commands like this. Because what it's going to do is it's going to add a bunch of packages here. And as a part of adding it, it's going to actually update the cache. And it's going to have a bunch of extra files. I don't want it to keep those files around. I don't want that to be part of my layer. And so at the very end, I say, and remove all those files that you just downloaded that I don't need anymore. So whenever you see people do something like that, that's them trying to keep the layer size small. And then it's going to create some symbolic links. And then here it makes a directory. And this one right here, this is just changing a setting on the container. That means if you start the container up, then your working directory is going to be in /app instead of just the root directory. There's other commands that you can use here. You can set environment variables, which I'm just commenting out there. So when you run a Docker file, the way that you would run this Docker file is you'd use the docker build command. So I can do that over here. Sorry, DevOps roles, Python, oh, come on. Arborian Python image, files. Okay. Docker. So there's a Docker file. So I can say docker build. Let's do a docker build -h first. So you give it the directory that you want to build this image in. And so that directory is going to look for a Docker file inside the directory. But what I want to do here is actually, so it's the current directory. And then I want to give it a tag. I guess let's do that first. So I'll call this one Tech Talk image. This is another way to build images. You don't just commit things, but you can actually use this kind of a process to build them. And so when I do this, it says, it sends the build context of the Docker daemon. So what that is saying is, if I wanted to copy files in from my current directory, there's special Docker file commands to do that. So it's sending you the context. That's everything that's here and any subdirectories. And then it says, from this, it says, I've already got that particular image, so I'll just use that. And it says, based on the image, you want to run this command. And so what it says here is, I've actually got an image that was created by running that command. So I'm going to use that cache, and that layer name is going to be this. And then this one uses the cache again, creates this layer name, does another command, another layer name, creates a directory, another layer name, sets the working directory, another layer name. And then this is the final image. And so if we say docker image ls techstar, we got the tech talk image there. Kind of funny, it says it was created 2 months ago. And that's because, actually, let's see if I can do grep 7179. So I'll zoom that in. So my Arborian base, I actually created 2 months ago, probably when I got my laptop back from the coffee incident. And in this case, it was able to just recreate everything based on that cache. Okay. So that's building things from images. most of our stuff will have Docker files already created, but that's how the Docker files are working. We use Docker files instead of doing things like interactively because it's reproducible. If you just write this Docker file, you're going to get the same image if you run the Docker file multiple times, as opposed to let's start up a container, run some commands, commit the container when we're done, right? That's a lot less reproducible. That's kind of a hacky way to do things. So in this way, we just modify this. If I changed one of these commands, if I inserted a command here, said run, echo foo, whatever that command was, everything here and below would be new images because it wouldn't trust this to have not changed something important. So if you change a single line, then everything at that line and below, or that command and below, will generate new layers for your Docker image.
Wait, so can you go over that again in terms of not using commits, or new images, but using a Docker file?
So yeah, so Docker file. Think of Docker file as a way to automate doing the committing. So when you run the Docker build command, Docker is actually going to take each one of these commands here, and it's going to spin up a container based on that command, execute something, and then it's going to commit that container. Right? Now, the other way that I can build images is I can just spin up a container myself. I can make some changes to it, shut down the container, and commit it. But if I did that, I'd have to remember all the different things that I did while the container was running. Right? So it's harder to reproduce that. It's harder to remember all the things that you did in creating that container.
And every time you open, if you did it the other way, committing the changes, every time you open that container, you would have to do the exact same steps in the exact same order.
Right. If you wanted to get the same image out as your result, yes.
So by using the Docker file, you're guaranteed that it's going to be the same.
That's right.
Be very predictable. I got a question. Okay, up top, you are specifying Alpine 310. That's from where your Python is coming, right?
No, that's the operating. So going back to that's like an Ubuntu, except it's Alpine Linux.
Okay.
So
now, if you didn't specify that, it's going to give you Ubuntu.
Well, you have to specify the base layer. You're required to do something to build off of a base layer.
Because I built a couple and I never specified that. I just said from Python 3.
So that is an image which is based off of Debian, I think. So that is and that's Debian Linux, that has Python installed in it already. So you were still doing something like that. You just were not aware.
I've got like a prepackaged Python that already had the Alpine or Debian or whatever in it.
Right. So I can actually say Docker run rmit Python bash. So it's now downloading this. And so you can see these different things here. These are the layers of that image. So that's why you see this. So some of these, it'll say the download's complete because I already had a cache copy or whatever. So it's going to download them, extract them locally. Okay. So it downloaded a newer image for that. So now if I say Python -- version, this is probably 3.9. Yeah. So, but if I look here, it's saying, well, this is actually, this is maybe not the best example because it is running on Windows. Actually, let's see if I can find out the Docker file. For Python. So switching over here. So this is what I actually just pulled. It was this image right here. Neat thing about this is it usually gives you access to I hope it'll give me access to the Docker file. That's kind of interesting. Lots of different versions of the image, it looks like. Would have been nice if it would tell me whether you let's see. Well, here's,
I see Alpine.
yeah, there is one that's based on Alpine. So here's a Docker file. Okay. So this is Python's Docker file based on Buster, which is that's a version of Debian. So that's the from command that it uses. Right. And then it sets some environment settings. It sets a few other environment variables, updates. So this one's using apt-get update as opposed to using apk-add. Apk-add is what Alpine uses. apt-get is what Debian uses. So it installs a bunch of things there. And then it actually is going to compile Python from source. So this is a single ginormous command because it creates a whole bunch of intermediate files and it doesn't want to save those. So it makes sure to clean all of that up. So you see here it says remove user source Python. So it removes everything that it uses as a temporary source file for building Python. Then it creates these symlinks. Make sure you get pip as well. And then it says, oh, by the way, if you don't specify any other command, just go ahead and run Python 3. If somebody just tries to run this container normally. So switching back up here, if I run this without bash, it's in Python. So that's how that was working. It's basically, that's just another image that someone's provided that already has Python installed for you.
Okay.
Okay.
And your Docker file, you're getting the Alpine, and below on the second run command, you're telling it which Python you want. No, that's which directory you're going to put it in.
So here I say I want Alpine. Here I say install Python 3 dev from Alpine. That's what that part is right there. APK add and upgrade if it's already there, Python 3 dev, and then a bunch of other packages that I want to make sure are always there. So that's how I make sure I've got Python. And then I create some symbolic links to make it easier to run Python.
What is your thinking when you choose whether it's going to be Alpine or Ubuntu or whatever? Like, what is your thought process?
So Alpine has it has a reputation for being smaller. That's a positive. Debian is maybe a little bit bigger than Alpine, but it's going to be smaller than Ubuntu. And so the downside to using Alpine is that, sorry, just checking to see, do I have an Alpine? It doesn't look like they do any Alpine builds. Alpine uses a different library for a lot of its code. So most Linuxes are based off of a library called glibc. And that means it's a very common shared library that a lot of the programs use. Alpine is not using glibc, it's using another library which is smaller, but maybe a little bit slower, called Musl, M-U-S-L, or Muscle. I don't know how you're supposed to say that. So all of the things that need to be compiled for Python, like if we're running pandas or NumPy or whatever like that, those we typically have to recompile for Alpine. So that's the downside, because normally people don't ship precompiled versions of their software for Alpine, at least not yet. So that was kind of my thought process is, I can figure out how to create these pre-built wheels. And so I'll just go ahead and use Alpine, and hopefully my containers will be really small. Now I've got gigabit fiber at home, and I don't care as much because pushing and pulling big images is not a big deal for me anymore. But that was kind of what I was going for at that point.
Okay.
Yeah. Now there's other things that we can talk about next time. I think we've been talking for an hour, so I don't know that I need to hit them now. But Docker Compose is something that I think would be good to get into. So Docker Compose means that Docker Compose can't do anything that is impossible from the command line, right? We could do Docker commands all day long, and everything would just work just fine, just as well. Docker Compose gives us another way of saying, hey, I'd like to have these 4 containers running and these volumes mapped on them and these environment variables, and I want you to give them these names and maybe even use these Docker files to build them. So you can specify all of that in one file, and you don't have to kind of memorize these cryptic command line arguments. So, but yeah, we'll save that for later. We can look at some of the details on how we can do Dockerfile stuff. Any other questions about stuff we've looked at here?
I'm probably going to ask again about the commit versus Dockerfile, but we can do that another time.
So I guess the quick answer is we don't ever commit in what we do. I don't think I do anything. Sorry,
I guess
there is a build process that we go through, and that's all done through Ansible. And I don't remember if Ansible might do a little bit of stuff with committing, but yeah, just think of it. Yeah,
I'm still thinking about all this kind of in terms of Git, and just as a commit is kind of how to save your work. And so I'm not understanding how your work is saved or changes are saved in a Docker file.
Well, Docker file automatically commits for every command.
Oh.
So when you build an image based on a Docker file, think of it as run this command, commit, run this command, commit, run this command, commit. And in the end, whatever your resulting image is, after you've done that final commit, you give it a tag.
Okay.
Sounds good. I will talk to you all later then.